Today we are going to look at magnets and magnetic fields. So the first question we should ask ourselves is, what is a magnetic field? A magnetic field is a region where magnetic materials like iron and steel and also wires carrying currents experience a force acting on them. When we think of magnets, we usually think of an image of a bar magnet, like so. You can see here that the magnetic field lines run from north to south, and that north is usually shown as a red colour, whereas south is usually shown as the blue. Some key things to remember. North and south poles are opposite and therefore they attract each other. The magnetic field lines will run from north straight to south. North and north are like poles or the same poles and they repel each other. And the same goes for south and south poles. They are the same, so they repel each other. So some key words from this is that north and south undergo attraction, where north and south undergo repulsion. So the next thing that we will discuss is the magnetic effect of an electrical current. So we have to go back to 1819 in Copenhagen, where Hans Christian Ørsted discovered that any conductor carrying a current has a magnetic field around it. However, he also noticed that when the current stops flowing through the conductor, the magnetic field disappears. So imagine the following image. You have a wire, which is the black line here, and I. I is a symbol that we use for the current flowing through the wire. The blue lines are the magnetic field lines. You can notice that there is no north and south pole for these magnetic field lines. They are going in concentric circles. So, how do we know which direction that these magnetic field lines should go? This is our next question that we will look into. For this, you need to use the right-hand thumb rule or the Maxwell corkscrew rule. In the following image, you can see the I, which again indicates current, B, which is magnetic field, and the use of your thumb. For this rule, point the thumb in the direction of the current along the conductor. So as you can see here, the current is moving in this direction, and my thumb is also pointed in the same direction. The next thing that you're going to have to look at is your fingers. Your fingers will point in the direction of the magnetic field lines. So here you can see that the fingers are pointing this direction, and that is the direction of the magnetic field lines. This works for a straight wire only though. So, what would happen if you decide to bend the wire around into a circular coil like so? Would this rule still apply? So let's have a little look at the following scenario. We have a circular piece of coil with current going through it. We will use the right-hand rule, and this will indicate the direction of the magnetic fields. So when we use the right-hand rule on this section of the wire, you can see that the magnetic field points inwards towards the coil. Okay, and this goes for every point in the wire. The magnetic field lines point inwards. So notice that all magnetic field lines are pointing towards the center of the coil. These magnetic fields reinforce each other, creating one greater or one total force for the magnetic fields. So the green arrow indicates the collective direction of the magnetic fields. Now, What would happen if we increase the number of coils? So as before, we have a coil here, but this time I decide to loop it more. So I'm increasing the number of coils. Again, we have current going in and going out. However, when we have a coil like this, we call it a solenoid. A solenoid is a length of coil of wire whose length is much longer than its radius. We again would use the right-hand rule to find the magnetic direction, which would point inwards for this example. So each one shows that if we do the right-hand thumb rule on each point of the coil, again, the magnetic field lines always pointing inwards for this example. This gives us a total or sum of magnetic fields going in the direction of the green arrow. So what we have actually developed is something that is very like a bar magnet. It will have a south and north pole. South, for this example, being at the top and north being at the bottom. The magnetic field lines going from the north to the south. So just like a bar magnet, this collective or sum of all these magnetic field lines will go from north to south. So, in summary, we can have a solenoid and a bar magnet which act very similar to each other. But when it comes to a bar magnet, we know the difference between the north and the south because the magnetic field lines go from north to south and the colour can indicate which direction is north and south. But how do we know for a solenoid? So the next question is, how do you know which side of the solenoid is north or south? So this brings us on to having a look down the solenoid. Imagine your eye is looking straight down the solenoid and you will see a circular shape. If the current is moving in an anti-clockwise direction, it is the north pole. So imagine the blue arrows showing the anti-clockwise direction. If we join them blue arrows together, it'll look like an N for north pole. However, if you look straight down and the current is moving in a clockwise direction, this would be the south pole. So again, point the arrows in a clockwise direction, join them together, it looks like an S, so S for south pole. This will allow you to find the orientation of your north and south pole. So, imagine now you have a solenoid and you decided to put a metal bar in the middle of it. Or an arm bar, should I say, in the middle of it. Okay, this would be an iron core. So an arm bar is placed in the middle of our solenoid. We again have a current running through it. The iron core will become magnetized when the current passes or flows through the solenoid. Iron is a magnetic material and can become magnetized. It is a soft magnetic material, which means that it can gain and lose magnetism. So when the current is switched off, the core loses its magnetism. So again, if you spun the current, the iron core will become magnetized. However, if you turn off the current, the iron core will become demagnetized. The solenoid and coil together is called an electromagnet. So the last question that we'll ask ourselves is what are the effects, what are the factors that affect the magnetism of an electromagnet? The first one that we'll look at is the number of coils, type of core used, different material can be more or less magnetized, the current flowing through. If you increase the current, you can increase the rate of magnetism. And then the temperature. Temperatures help the flow of current. If you increase the temperature, you'll increase the rate of current, which therefore increase the magnetism. And finally, some uses of electromagnets. So the first one is in bells. So like the school bell, it can be used through an electromagnet. Second is in relays, which is a safety device allowing us to use low current circuits to turn on high current circuits in a safe manner. The third one is lifting scrap iron and steel. And then the last one, which is used for motors, which we will have another video on. Please look over each one of these examples, and a good site for this would be BBC Bitesize. Hopefully this is of some help to you.